This video is a very brief introduction to optimization. It corresponds to section 2.6 of the Applied Analog Electronics textbook. Now, the basic idea that we're going to be dealing with is that we have a function, say of a single variable. Now, this can actually be a function of multiple variables as long as we're only doing the optimization with respect to just one of them. And what we're going to do is to look at this thing, and we want to find the place where it's maximized. And that can be either at a place where it reaches a peak or at one edge of our space. If it's only defined in a certain region, we could be hitting the boundary of that space. So there's two places that we can look for a maximum. Either a place where we have a flat spot where the derivative of 0, or at a boundary of the space. And given that this is a one-dimensional optimization problem, the boundary of the space are just pretty much the beginning and ending intervals. So this is a very simple sort of optimization problem. There are much more sophisticated optimization problems, optimization problems with constraints, optimization problems with multiple variables, and there are entire courses taught about how to do approximations and how to do optimizations that are exact in all kinds of different variations. We're only going to deal with the very, very simplest cases, the ones that you can do with the amount of calculus that we had in the 8-minute summary in the previous video. So, this simplest version. Let's do one example just to see how it works. Let's say we're trying to optimize x cubed minus 27x. And we're trying to optimize this over the range 0 to 5. Well, we can take the derivative of this and get 3x squared minus 27, set that equal to 0. We can divide out by 3 to get x squared minus 9 equals 0. And that means x equals plus or minus 3. Well, there's only one of those in this region, so we say x equals 3. Are we done? Not quite. We need to also consider x equals 0 and x equals 5, because we don't know that this is necessarily a maximum. In fact, why don't we take a look at this thing with GNU plot. All right, I've got f of x here, x cubed minus 27x, and I plotted it. And if we look at this thing at x equals 3, we don't seem to be at a maximum. We seem to be at a minimum. So that's not the right answer. And we can print out the different values here and see that at 0, f of 0 is 0. We could have told that anyway. X cubed minus 27x is going to be 0. At 3, we've gone down to minus 54. And at 5, we've gone down to minus 10. So the highest of these three numbers is the 0. And so going back to our previous thing, this previous guess was wrong. We are in fact here in a case where x equals 0 was our optimum. Now, if we'd had a different range here, a range that included minus 3, for instance, it might have been different. And in fact, we can take a look at that plot again and see that 0 is not our maximum if we have a wider range. If we had all of minus 10 to plus 10 here, we would have a different range. And so let's try printing f of minus 3 and f of 10. And now we can see minus 3 would have been the maximum if our range didn't go as far as plus 10. If it only went as far as plus 5 like we had before, then minus 3 would have been a maximum. But if we can go all the way up to plus 10, then f of 10 is our maximum. So when you're doing optimization, always pay attention to the boundary conditions. What's the minimum and maximum value for the variable you're optimizing with respect to? Because those may very well be the interesting cases. It might not have an optimum within the range you're looking at other than at the boundaries. Okay, that's about all we'll be needing to do with optimization in this course, so that's it for this video.